The capture and use of CO2 for the production of fuels and chemicals has become increasingly significant. Various methods have been developed to transform CO2 into valuable chemicals such as syngas, methanol, dimethyl carbonate, diethyl carbonate, and polymers. Diethyl carbonate stands out as a versatile compound with applications as a fuel additive, solvent, and reactive intermediate. This video demonstrates a direct process for converting CO2 into diethyl carbonate. In this approach, CO2 reacts directly with ethanol to produce diethyl carbonate and water. Additionally, 2-cyanopyridine is introduced as a dehydrating agent, which reacts with water to form 2-picolinamide. By continuously removing water during the reaction, the conversion efficiency is significantly enhanced. 10 components are involved in process simulation. These are carbon dioxide, ethanol, diethyl carbonate, water, 2-cyanopyridine, 2-picolinamide, ethyl picolinimidate, ethyl picolinate, ammonia, ethyl carbamate. The slide shows the reactions involved in the process. The direct conversion of CO2 to diethyl carbonate is represented by reaction R1. Carbon dioxide reacts with 2 molecules of ethanol to produce diethyl carbonate and water. This reaction is a reversible reaction, meaning it can proceed in both directions. Reaction R2 represents the reverse of R1. It can reduce the overall yield of diethyl carbonate in the process. R3 involves the conversion of 2-cyanopyridine to 2-picolinamide through hydrolysis. The consumption of H2O by R3 favors the conversion of CO2 to diethyl carbonate. R4 influences the process like R3 but in the opposite direction because the reactant ethanol is consumed by the reaction. In R5, the product 2-picolinamide from R3 also reacts with ethanol and also negatively influences the process. R6 is the reverse of R5. It can limit the ethanol consumption through the forward reaction. R7 involves the interaction of diethyl carbonate with 2-picolinamide, resulting in the formation of ethyl carbamate and ethyl picolinate. This reaction is a side reaction that can consume diethyl carbonate, potentially reducing the yield of the desired product. R8 is the reverse of R7, showing the conversion of ethyl carbamate and ethyl picolinate back to diethyl carbonate and 2-picolinamide. R9 shows the hydrolysis of ethyl picolinimidate to ethyl picolinate and ammonia. This reaction influences R1 positively through the consumption of H2O. The slide shows the kinetics of the reactions. The kinetics have the Arrhenius form. The activation energy is a crucial parameter in determining how sensitive a reaction is to temperature changes. A lower activation energy indicates that a smaller amount of energy is required to initiate the reaction, and thus the reaction rate will be more sensitive to temperature increases. Reactions with lower activation energies, like R3 and R6, will be more sensitive to temperature changes. This means that increasing the temperature will have a more pronounced effect on their rate. Reactions with higher activation energies, like R1 and R2, will be less sensitive to temperature changes. The values of frequency factor vary significantly across the different reactions. A higher frequency factor generally leads to a faster reaction rate, as it implies a greater number of effective collisions per unit time. Reaction R2 with a high frequency factor has a high probability of occurring if the temperature is sufficient to overcome the activation energy barrier. Reactions with lower A values, like R4 and R5, have much lower frequency factors. This suggests that even if the temperature is high enough, the likelihood of a successful collision and the overall reaction rate for these reactions might be lower. The mole fractions of reactants influence the rates of most reactions, except R1 as it is presented in the given equations. R2 is unique in that it is also influenced by the mole fractions of the product. Generally, higher mole fractions of reactants tend to increase reaction rate. This is a fundamental principle of chemical kinetics. Increasing the concentration of reactants usually leads to an increase in the reaction rate. R2 is influenced by the mole fractions of both reactants and product. Higher concentrations of products drive the reaction in the reverse direction. Among the components involved in the process, there is no built-in data for ethyl picolinimidate, therefore it is defined manually. For ethyl picolinate and 2-cyanopyridine, property parameters are missing. The next slides show the parameters, which we will enter into Aspen Plus. PLXANT is an abbreviation for Polar Liquid Activity Coefficients with Antoine vapor pressure. It is a parameter block that contains extended constants for calculating the vapor pressure of a substance. These constants are specifically tailored for the Antoine equation, an empirical relationship linking a pure liquid's vapor pressure to temperature. DHVLDP stands for DIPP are heat of vaporization coefficients. It's a parameter block within Aspen Plus that houses specific coefficients used to calculate the enthalpy of vaporization for a pure substance. These coefficients are sourced from the DIPPR database, a comprehensive repository of thermophysical properties for pure substances. CPIGDP stands for DIPP are ideal gas heat capacity coefficients. It's a parameter block within Aspen Plus that houses specific coefficients used to calculate the isobaric heat capacity of an ideal gas. We will now simulate the reactor for direct CO2 conversion to diethyl carbonate. Here are the reactor specifications. Reactor type: reactor with constant thermal fluid temperature. The reactor is simulated with a constant temperature of the cooling fluid. This is a type of reactor setup, especially when precise temperature control is desired for the reaction. Heat transfer coefficient: 100 watts per meter squared Kelvin. This parameter represents the efficiency of heat transfer between the process fluid and the cooling fluid. A higher value indicates better heat transfer, which can help maintain a stable reaction temperature. Thermal fluid temperature: 125 degrees Celsius. This is the temperature of the cooling fluid. Reactor length: 4.11 meter. Reactor diameter: 1.5 meter. These dimensions determine the reactor's volume. Valid phases: vapor-liquid. Particle density: 1,500 kilograms per meter cubed. Bed voidage: 0.8. The diagram shows the concentration profiles for components involved in the process within the reactor. We can observe that the concentrations of the components change significantly along the length of the reactor. The concentrations of DEC, PA, and EPI rise steadily along the reactor length. The concentration of EC, EP, and NH3 first increase relatively sharply, but their increase tapers off after a certain point. The concentration of NH3 even decreases. The feed components are consumed along the reactor and their concentration decreases accordingly. The product water is depleted as desired. The diagram shows the temperature profile in the reactor. The temperature rises steeply at the beginning of the reactor, reaching a peak of approximately 155 degrees Celsius. The maximum temperature marks the point with the most heat generated. Beyond this peak, heat generation starts to slow down. The provided calculations in the slide represent key performance metrics for the process. CO2 conversion indicates that 59.46% of the CO2 fed into the reactor is consumed during the process. DEC yield reflects the proportion of CO2 that is successfully converted into the desired product, DEC. DEC selectivity indicates that 97.97% of the converted CO2 lead to the formation of DEC, with minimal formation of byproducts.